more simple pressure reducing, which is the proportional PRV, okay? And now we will talk about more sophisticated pressure reducing. Could be more sophisticated, because if we want dynamically to change the setting of the pressure reducing, this is something we can apply, and it's one of the solutions that we give when we talk about municipal delivering water to household, okay? So actually, water utility is obligated to supply, hopefully, 24/7 water to the household in a sufficient pressure. Also, to the critical points. Same as in irrigation, we have critical points, the most distant point, the most elevated point. So we need to make sure that we are supplying water at sufficient pressure. I know that in India, it's going towards 24/7 as well for all locations and area. So probably it's something that important to you. In Israel, the pressure that the water utility is required to supply is about 2.5 bar. I know it's India, it's less, 1.2 bar, something like that. So actually, when a water utility or a design company is designing the water system for an area in the city, it should make sure that the critical point will get sufficient pressure. Even at peak demands, when we have high demands, for example, in the mornings or in the evening when people come from work. And due to that fact, many times along the day, other areas in the DMA get excessive pressure, which is not required. And this excessive pressure is increasing the non-revenue water, what we call non-revenue water. Non-revenue water is the water that the water utility is losing along the way and is not getting the bill for, okay? And it could be, partly it is from leakages in the system, okay? Because many times the pipelines are quite old, okay? Could be 50, 60 years, and we have cracks, and we have joints which are not completely sealed, and we have leakages and we lose the water. So in order to make this system more efficient, cost efficient, saving in water, saving in energy, we need to reduce the leakages, okay? Some leakages are very apparent. We can see it because it's above ground, and some leakages are hard to detect, okay? And they are below ground and that are less capacity also of water. So the issue of high pressure, excessive pressure in the water system is causing us to lose water due to leaks. It can also increase the risk of pipeline burst, okay? When we have all the time excessive pressure, you can find in the Google all kind of researchers that connected the pressure in the night in the DMA to the chance of burst in these systems. You can find these graphs and results, okay? And there is the issue of the reservoir overflowing and the robberies, and that is less our issue today, okay? When we talk about DMA. So what we want to do is to decrease the excessive pressure, okay, throughout the day when it's not needed. This is, you can see here very quickly, the non-revenue water in different countries. It's quite old graph, I think you see the years, okay? But you can see that some water utility even lose more than 50% of the water are non-revenue water. So they are losing money, energy, water, and etc. There is actually a thumb rule that if we reduce the pressure in 10%, the excessive pressure in the DMA, in the municipality, we will reduce in same ratio, about 10%, the leakages in the system, okay? I will skip this because it's not really important. So when we have high pressure in the pipe, excessive pressure, you can see how the leak looks like, okay? And this is showing very nicely what happens when we talk about low pressure, not excessive pressure, and how the leak looks like. And we are losing much less water, okay? So why we want pressure management? I already said partly to save money, to save water, to save energy, to save the issue of maintenance. If we have pipe burst, for example, we don't need to frequently detect the leakages, because some of the solution is to actually use method to detect the leakages and fix them. We prefer to prevent it, okay, by optimizing the pressure in the DMA, okay? Another important thing, as I said, and I will say also about surge analysis, about Bermad air allocation and sizing, Bermad is capable of helping and supporting a comprehensive analysis of a specific DMA, of a specific system, okay? In order to optimize the solution that we offer you, okay? So this is very important that, again, we want to be inside with you in the project, not just, you know, you tell me a diameter, you tell me a valve, I give you valve. It's not like this. It's not how we think we should do the business, okay? So taking into account to explore the daily flow pattern, because it can vary, for example, between weekends to days of the week, when we have a special holiday, when we talk about industrial area, we will see peak in pressure, okay? So we can explore all this daily flow pattern and analyze it in order to give the most cost-efficient solution. When we talk about minimum night flow, this is very important, because when we will apply our pressure management solution, we should compare the minimum night flow before the solution and after the solution. And this gap will actually give us what we saved, okay? How much water we saved, how much money we saved, how much we reduced the non-revenue water. Of course, changing in flow and pressure and system efficiency, all of this we should evaluate and analyze before we give a solution, okay? I put this graph because it shows typical consumption in a municipality. It's very different in irrigation. In irrigation, you will see steps. You will see very dramatic changes. Okay? Because you have a big shift and a small shift, and it's opening and closing. When we talk about the municipality, it's changing towards the day, and we can actually even anticipate the peaks of demand in the morning, in the evening, okay? And the decrease of flow in the night, okay? I can say even when we talk about working class and upper class, they will act different flow patterns throughout the weekend, for example. Upper class will go for some vacation, workers will stay at home. Okay, so we need to take all this consideration and make the analysis. There are different approaches to DMA. In the past, one DMA could have different pressure source in order to have a backup, okay? So if one pressure source is not working, we have the other one. And nowadays, I think it's going more and more towards isolating each DMA with its own pressure source, okay? And this is because it will make it easier to make the water balance on this area, okay? And to give the most technical and cost-efficient solution per this area. Okay, let's continue. So this is the critical point, right? You can see here the critical point, okay? And we need to now to supply water to this entire DMA and making sure this critical point will get sufficient pressure 24/7 at peak hours as well, at rush hours, when demand is high. Okay, so if we apply the first very basic solution, standard PRV, we talked about pressure reducing valve, right? If we apply it, it will already solve 70% of the issue. Okay? Why? Because before we had nothing. We had this high pressure because we wanted to supply to the critical point. And now we have a pressure reducing valve which has adjusted and calibrated to a certain setting. Okay? So this valve will make sure that at the downstream of the valve, we will have a constant pressure of 45 meter, okay? And this will ensure that during peak hours, okay, of the day, the pressure will not drop below, for example, 2 bar in the critical point, in the household of the critical point, okay? So it will be the minimum pressure, optimizing the pressure that I can apply on the system, and not 6 bar and not 7 bar, okay? And this way I will reduce what? The leakages, okay? I will reduce the leakages and I will reduce the water that I'm losing, okay? So let's continue. And if we want to make this solution even more sophisticated, it can be connected, okay, to a timer, and we can change the setting between day and night, okay? We will have a day pilot and a night pilot, okay? And it can even be connected to a flow meter and change the setting dynamically according to the flow. So it will actually follow the consumption like a mirror, okay? It will change the setting, okay, automatically by connecting the valve to a controller, and it will change the setting according to the consumption, and this will give us all the time, okay, 2 bar at the critical point, not just in the rush hours, okay? Because in the previous, if I go to the previous, when we are not talking, we're talking about the nights, the pressure is high in the critical point when the demand is low, okay? It's 45 meters, they don't need it. The minimum required is 2 bar, okay? So here, we are taking care in a very sophisticated way. We need to take this into account that it's more complex, it's more sophisticated to understand. We are taking care all the time to apply the 2 bar on the critical point, okay? And reduce the leakages. So this is a summary of actually the solutions, going from the most simple to the most advanced one, okay? For pressure management, we have the standard PRV that if you apply it, I said you already, so you are improving the situation 70% or 80%. You can use a day-night pressure reducing valve that will have 2 pilots, one for the day, one for the night, with 2 settings, and a timer, a controller which is based on time, changing between the set points. And the more advanced one, which dynamically changing the setting, okay? At the end, you will get the presentation. You will get the presentation, don't need to. So it's connected to a controller, okay? And this controller is actually controlling an hydraulic device that is changing the setting. It's like you will come and change yourself, but it's done automatically because this controller is connected to the valve controller and also the flow meter. Okay, so it changed the setting dynamically, automatically. Another option is electronic valve with 2 solenoids, what we call a 780, and it's like a 420 milliampere valve. Okay, it's an electronic valve. It consumes electricity, energy, and so on. This is the day-night control loop, okay, according to timer, okay. And I want Lior to say something about this automatic solution that are connected to a controller.
Okay, so basically, the entire concept are similar, and the only thing that we add with the digital is the ability to do the changes remotely. So instead of going to the pilot and change it with a screwdriver manually, the controller gives you the option to do it from remote, and then from remote you can do it as a fixed method, or you can do it as a dynamic method. Okay, this is depend on the level of the controller, but in the end, the controller gives you an output based on the and what you improve is the scheduling. You make the scheduling not just day and night, but also the dynamic one. So here we have a very simple controller that, by the way, as far as I know, we are going to phase it out because we have a better solution that I will show you in a minute. And you see that the pilot is advanced here, okay, because it has also the electronic part. And this controller actually operates the pilot during a night. So once it's open, and during the night, it changes the setting. 2 points. Okay, just two points.
For peak demand, for flow demand. Okay.
Now we come with a new. Yes. Now we come with a new solution which we call Epsilon. Okay. This is the new product that we. Okay. We have an animation program, but think that the X is staying there. We have a new solution which is called Epsilon. This is this gray or dark gray box. And the solution is very simple. It's come to replace this simple controller of on-off. It's also can measure 2 analog inputs, and it has a pressure sensor. So this unit, the Epsilon, is connected also to the ports and read the pressure all the time. And we will show you in a minute, in our cloud, it's not only changing the setting point according day and night, it's also provide you a lot of information about what is going on in the valve, with the valve. What is the pressure, the inlet pressure, the outlet pressure, what is the flow rate, of course, the quantities, when the changes are made. So you got a full information about the operation of this area, and then you can make a decision. Once again, in this stage, make a decision by yourself. Someone has to go to the computer, see the graphs according a few days or weeks or months, understand the pattern, and then configure the Epsilon to this pattern.
Optimize the pressure that we are applying in the system.
Of course, each one of you can understand that in the future, we can create this automatically as well by machine learning, artificial intelligence, and stuff like that, to learn automatically the pattern of this specific area, of this specific city, and optimize this even more.
Okay, I will say something short about this, and then we have another application with the controller that Leo will explain. This control loop, I think it's very suitable for India because it overrides the pressure management on peak demands. And I know that in India, pressure is an issue. So we actually, in peak demands, we're suffering from very low pressure. So we can override completely the control loop, and the valve by the solenoid. You see here a three-way solenoid. You see here that the solenoid is open to the atmosphere, so you can fully override the control loop, open the valve completely, and it will be like transparent with a negligible head loss, and you will transfer all the pressure you have in the flow during the peak hours. When we are going for night hours, for low demand, okay, we de-energize the solenoid, okay, and it will connect back to the control loop and will reduce the pressure with the reducing pilot, okay? So this is good when we have low pressure.
Yeah, we got in the end graph like that. When the demand is going down, the pressure goes down with it, and when it goes up, of course we give the maximum pressure. Okay, so this is the important solution. We have short time, but this is the important solution that we release in nowadays, which is called Delta. Okay, so you see we took the way of Greek letters. So actually the Delta can work as a standalone or together with the Epsilon that we saw before. Okay, and the Delta has a built-in 2 pressure sensors and one operational mechanism. The pilot here, as Sarit explained, is it's a pilot, but it's a different pilot. What is the difference? That once again, instead of screw that I have here I have a kind of inside, kind of a simple motor that push the spring according to the.
You can see it in the control loop. You see?
Yeah, according to the current that it got, okay, from here. And then all I have to do, and this unit of course has a communication, it has a cellular modem inside. So all I have to do is transmit from far away what should be the level of the spring, and it can be done automatically. So if I have, and we have in the Barmat Cloud software, that there I define whatever schedule that I want, okay? And then it's automatically, if I define that in 6 o'clock in the morning, the pressure should be reduced to that level, and in 8 o'clock it's going to that level, and in weekends behave in this pattern, and in holidays behave in that pattern. Everything is on the cloud, not automatically when the time comes, the Delta, this unit, got the information and change the setting automatically, okay? Also in the other direction, once again, it's connected to the pressure sensor, connected to the upstream and downstream of the valve. And if I have a water meter, the unit connected to the water meter as well. So I got all the information in real time on the cloud, what is going on. So when I said that this unit can work together as standalone, if it works as a standalone, I put it on the main valve in the entry of this pressure area, and I control it like that. If I want to fully operate the system, I can put epsilons, the small units that you saw, all over inside the area. Okay, I got all the information, and then I know if my pattern, the pattern that I defined to this unit is correct. Okay, because I see also what happened in the endpoints of the city. And based on this information, I know that I need to increase the pressure or change the hours or change the anything else.
Even set like special programs for special days, holidays, whatever. You know, we all have the days that we are fasting, the day we are celebrating. So yeah, you can make a special program.
So now we release this unit. We have a few tens of these systems all over, and there is a big excitement about this solution because it's really efficient. You know, to do such a thing, theoretically, it's not such a big deal. Any startup maybe can do it, but the hardware inside this Delta here is very sophisticated, mainly to be able to do it in very low pressure.
I have a question.
So you have a question?
Yes.
Yes, please.
I wanted to ask you what is the minimum delta which can be achieved based on the inline pressure? So if I have an incoming pressure of say 40 meters or 4 bar, can I release something as much as like 38 or 36 meters? So that's a 0.4 bar delta. Is that something that this valve is able to do, or is there a minimum delta that this valve needs? And my second question is, what is the head loss in this valve if the valve is completely open? So if I'm just sending water through the valve, based on your test bench data, do you have any head loss, even if it's 0.1 meter, but do you have any head loss across this valve?
First of all, I say about the head loss. Berman has the KV graphs, okay, and has a Berman soft, okay, and they give the head loss in a certain flow rate to a certain valve series in a certain diameter. So if the flow velocity is not as we usually design, okay, then usually the head loss will be minimum and negligible. One, I don't know, if you increase the flow velocity 2 meters, okay, so the valve, this is what we say, that the valve is fully open and fully transparent, okay?
But totally agree with Sarit, but generally speaking, in this solution, we didn't touch the valve at all. So it's the regular 700 valves of Berman, and the same performances that we have with this valve is together with the Delta. No change in the performances or the limitation of head loss or stuff like that. Okay, so what you can choose the right version and
according to your flow,
yeah.
pressure.
I have a completely different question. I'm like, since we say that this delta is it is able to connect with the cloud and can do scheduling, does this delta have its own brain? Because in India, if we are supposed to install similar kind of system, but this question is if there is no signal or connection to the cloud, does that delta have its own brain to store the schedule which was given previously?
yeah.
Yeah.
No, say yes, because it's very good question. No, this delta is a controller. By the way, it's the same concept with the omega. Omega is for irrigation and this for a water hole. But inside there is a full controller that got the scheduling. Okay, so if there is no communication or stuff like that, the unit keeps works according to the last information that it got. So it will close and open according to the last. You won't be able to make changes to the pattern, but it's still working. And also there is, of course, a memory and stuff like that inside. So there is a log of all the information, and once you have the communication back, you got all the data back to the cloud. Okay, so you lose nothing. Also important thing to mention about it is that when you have the application with the cloud, there are other challenges of cyber security and stuff like that. You know, maybe you said in the field, nobody cares about my sugarcane or tomato, and nobody will try to pick my system and change the valve. Why someone will do it maybe for a play, but if you deal with the city water, you don't want that anyone will go into your system and start to play with it and drive all the people crazy. So our cloud is fully secured. It's very important to mention, and protected from security, from cyber attacks and stuff like that. Okay. Of course, all the time you have to work on it, but we are aware of this issue and we protect the cloud.
Also the issue of authorization.
Yeah, authorization, of course, it's part of it. Yes, sure. So this is just a nice view of how you see the information on the cloud. Once again, there are many screen here, and let you make analysis and make some insight and decision.
This is a standard PLV installation, you can see here. If we continue, we see some more application installation. This is a day and night PLV, okay, based on timer, okay. And you see here the PCBU, the multi-setting, the device which is sitting on the pilot, okay, and changing dynamically the setting according to the flow pattern.
Yeah.
Here it's connected to other controllers, not Bermat controllers, okay, but the Delta is doing the same job, and this is the electronic two solenoids operated PLV.
We didn't talk about this solution because to be open with you, we have this solution. It's very similar to what our competitors have, so we also have this solution, but we not suggest this solution. We think that it's inferior to the solution of Delta, and here it's very simple. There are two solenoids. One take the water out of the control chamber, one take the water in, and then if you have a pressure a flow sensor, you just play with filling up and emptying the control chamber. This is the way that you control the pressure. This method works, but usually it requires a lot of energy.
It also requires a controller that will get either the downstream pressure or the flow, and will change the position, the degree of opening of the valve according to the data. Okay?
So once again, we cannot go too much deep, but the solution that we bring now with the Delta, it's much more accurate. It can operate in a DC environment where you don't have any electricity around, so it's very efficient. You don't have to use a very big solar panel or stuff like that. And it's also more reliable in cases that something fell in the electricity, the valves keep working, unlike this method. So we have this method, and if someone likes it, we know how to sell it, but it's not our preferred solution. And this is one installation of the Delta. I guess it's in Israel. Here you can see it. Everything is blue.
And connected to the water meter.
Some other, mainly in Israel. This is the first line. Now we have also in the UK and in the US, I think, and in some other places. And yes, it's a very exciting solution that I think that it was to go to this world, because once again, it can bring a lot of benefit to cities that suffer from non-revenue water.
Okay, we want to continue, right?
Yeah.
Yes. Okay, so this is my favorite part. My favorite valve, pressure and flow control applications, not only at the outlet of the system, also in the upper network, rather than putting BPT. And I started this concept, we started together with Bermat India when Amay was in Bermat. So this is really something I think Amay will also have a great appreciation to. So this is a irrigation map, and what we want to do is go from the plots, which is for you is the OMS, to try to go back and to give Bermat solutions when we go back to the water source as well, okay? And this is something we managed to do really well in a cooperation with you, with your company. Farstad was in our place for a seminar, and there was another guy with you, right?
Yeah.
Yes? Hi. And I will talk about this case study of package 21 that shows us both solution of outlet management system and the upper network. Okay, so when we talk about a lift irrigation, an OMS project, we can zoom out and we can see we have a pumping station, okay, with Bermat solutions. We will talk about it later. A rising main, okay, and distribution lines. Each distribution lines, in this example, can irrigate a 500 hectare zone, and from the distribution line we have outlets, okay, to a 30 hectare chucks, okay, and in each 30 hectare we put what we call in India OMS, outlet management system. In France we call it cabinets. In other places we call it hydrants. It's all the same concept, same features, same applications, just the structure of the cabinets of the OMS looks different. And I continue. Okay, so this is, you will see it in bigger later. This is how a demo OMS on a 30-hectare tract look like. We made a demo, Bernard India made a demo in the field. And at the outlets to the farmers, the last hydraulic valve on the field is this valve, the pressure and flow control 100 series, that you also have it on the table here, okay? And it's in charge of an area of 5 hectares of irrigation. Usually 5 hectares is 5 farmers, something like that, right? The average for a farmer is 1 hectare. So after this hydraulic valve, we have some pipe going 100, 200 meters, you have it, you know it, you design it, with manual valves to the farmers, okay? And at the beginning, of course, we were making drawings and 3D drawings per each OMS, okay? So you can see the OMS this is the inlet to the OMS, okay, from the distribution line, yes? This is the strainer, a stone trap, as we said, air valve, combination air valve for air management, okay? Water meter for 30 hectares, okay? And then we have the, I call it, okay, the plot valves, okay? Flow and pressure control. We can see here the local controller, okay, per each OMS. Okay, now we put the omega, okay, in each OMS. And it's actually talking to a main controller, okay? Each local controller will talk at the end to a main controller. For example, in package 21, we supply 3,800 OMSs like this. Okay, so each one of them at the end talks to the central controller. And we have solenoids, left solenoid that operates the hydraulic control valve according to irrigation scheme, the shifts that you call it the control philosophy. I like this very much. So each solenoid is operating and energized only when we open, for the second that we open and close the valve, okay? It's very low energy required, and this is why we can use a 5-watt solar panel, which is quite small and can be stored high, protected from the wind and from the people who wants to steal it, okay? So this is important. And this is the demo in a bigger view. And this is the OMS in package 21, right, Pushkar?
Yes.
And you can see that the protection box is concrete here, and not some kind of metal or and maybe Pushkar wants to say a few words.
Yes, so as Sarit told, every 5 hectare almost we are sending an 8 LPS flow here. And there is a rotation management also we adopted, that out of, you can see this is a typical 20 hectare chuck. This is the inlet line coming. There is the isolation valve, then there is a strainer. This is a water meter, and these are the all flow control valves which we showed in the morning. So there is a rotation management is adopted such that whatever incoming flow will go to the single valve of 5 hectare. So that is around 8 LPS flow, and around the valve size we selected is around 50 mm or 2 inch with large body. We will share our catalogs, you will come to know what size we are giving for this flow. And this 8 LPS will go to the every 5 hectare, and then again there will be manual valves at the end of 5 hectare where farmers will utilize this water. And after a particular time is over of this valve will be closed and next valve will be opened. So how this will be done, that there will be a solenoid is given for every valve. Okay, and this solenoid can receive a command of on and off as per the schedule through this controller, which is mounted on the box of the
To say that I don't see here the solenoids. in this particular photo.
Yeah, next maybe
Yeah.
picture. So this is how the this controller looks like. So in OMS we take some inputs also, like we take an input from the water meter, what is its reading. So this will go to the RTO and you can take the readings in your control center. Again, there will be a pressure transmitter will be also mounted at the on this outlet manifold. So it will sense the pressure, and again you can record this value to the control center. And third function is that to on and off the valve. So all these three functions are happening through this controller, which is mounted on this. And as you know, the entire regulation, pressure and flow control is happening through the valve itself. So you don't need a huge energy for the regulation of the system. You need an energy only on and off the system. That's why the power consumption or the solar panel used for this is very less, like 5 watt.
Also, it's important, I don't think I put it in the presentation today, but this flow control method, the paddle, it's unique for Bermad because it's not creating structural head loss like you know in other flow control methods, for example the orifice, okay, and a differential pilot. When you put an orifice with a fixed machined hole per your design flow, you're creating structural head loss all the time, even when you don't need to limit the flow, okay? So the first benefit that it's not creating a structural head loss. Only once the flow velocity will be very high, it will push this paddle here, you see it inside, and it will push a mechanical mechanism inside that will change the water passage in the pilot, and this will command the valve to throttle close and limit the flow. Okay? So another thing, orifice is custom made per your project, per your flow setting. And if you want to change the calibration, it's very limited. Okay? So then you probably will need to change the entire orifice size. Here, you can versatile, change and adjust the calibration on site by using the calibration bolt. Okay? So this is important. And of course, when the valve is not limiting the flow and not reducing the pressure, it's a three-way valve. It's fully open, it's transferring the pressure that you have and the flow that you have. Continue. Okay, so I think we covered everything, right?
Yes.
Just isolation valves for maintenance. You can see here, you can see
Solenoid system.
the solenoid valve, okay? And I have nothing else to add unless you want to add something. It's clear, I think. Okay, so I put this slide just to explain when we need flow control. When we need flow control feature is when we want to protect the system and also the end users to make sure that they will all get equal rights for the water when we have an exceeding demand, okay? So when we are about to have an exceeding demand and overconsumption is when the users are not using according to the control philosophy, according to irrigation shifts, okay? And we cannot control the farmers. We can only punish them by reducing the pressure, because once we limit the flow, the pressure to this consumer will drop. And you need to understand that even though you are controlling the flow, you are affecting the downstream pressure, okay? Whenever a valve is regulating, it's closing. So it's affecting your pressure no matter what it does. Sustaining, reducing, flow, okay? So you call it flow, but you affect the pressure to the user, okay? We can have exceeding demand when we talk about burst, okay? So it could give us an indication when we limit the flow that something is wrong in the system, that we have a burst. And this is one of the worries in package 21 as well, that we put the flow control in a higher level in the system, in the upper network. Because usually we recommend to put the flow control as the last feature in the field. Why? Because we don't want to limit the flow when it's not needed, okay? We want it to be a safety feature. okay? Flow control valve is not supposed to limit the flow all its life. Pressure reducing, yes. Pressure reducing will reduce the pressure throughout the operation of the system. But flow control, no, it's a safety feature, okay? Because it also depends on the controller, on the type of pilot. But if we are applying three-way control, the pilot has an hysteresis, okay? It will start to limit the flow when it's needed, and the flow will start to reduce, and it will need to fully open again. And it will take time until the valve will react, until the pilot will react. And it could be in a situation that we are limiting the flow when it's not needed. So we don't want to do it when we talk about the upper network for no reason. We want to do it at the end, to the farm, okay? Because otherwise we create head loss for the entire system, okay? So this is important, but we can overcome this issue like we did in package 21. We can calibrate the flow setting 30%, for example, above the design flow. So only when there is a colossal case, something really went wrong, someone stole the OMS, the automation doesn't work, okay? A burst happened, then we will regulate, okay? Only in colossal cases. Also, when we fill up the line, okay, we want to have a control line fill up so we can limit the flow, okay? And when we have a change in irrigation shift, it's important in irrigation sometimes. One irrigation shift is over, but it's not closed yet, and the other one is already opened, and we will have exceeding demand, okay? And when a very big consumer is going in, for example, we fill up a reservoir. So we don't want the farmers on the way to the reservoir to get no water. Okay, we still want to supply them the right flow and pressure, so we can limit the flow that fill up the reservoir. Okay, for example, if you have a net of a lot of reservoirs, 20 reservoirs, 30 reservoirs, 1,000 reservoirs in Avinashi, then flow control will be much more easy to apply than pressure sustaining. Then we will need to run a lot of virus situation, dynamic, static, whose reservoir is working well. Flow control will be easier to apply. Okay, so actually, flow limiting valve is protecting the system from overconsumption and forcing all the user to be obligated to the design boundaries. And this is very hot subject, not only in India, because I told you all over the world, consortiums, water association, become very, very important player in the irrigation field, in the irrigation sector. This is the valve 100 series, okay, suitable for hard water like we have in India, with the minimum head loss, I can say even negligible head loss when it's fully open, operated by a LED solenoid and the hydraulic flow control. No need of communication or energy to limit the flow. This is, you can see here better the pilot, okay, that we showed you. So actually the flow velocity is hitting the paddle here, and if it's high flow velocity above the setting of the calibration of the pilot, this entire mechanism will be pushed against the force of the spring, and it will change the water paths in the pilot. That will change the degree of opening of the valve in the main line. Okay, and it will limit the flow. And also, when we talk about orifice, we have the sensor of the flow, which is the orifice, and we have the pilot, the differential pilot. Here, it's only one unit, integrated unit of sensor and a pilot. Okay, and as I said, it's easy to recalibrate and change the calibration at the site. So let's talk about package 21, upper network solution and the OMS. This is a map of part of the project, right? I'm correct? It's only part of the project. Pushkar, if you want.
Total project is around 80,000 hectares. This is a lift irrigation project, lifting water from the dam. There is pumping station, and entire network is a pressurized pipeline network. And there are two pumping stations. There are two zones, like one is Gadkol and another is Metapalli. So as you see, there are total 80,000 hectares. I will just briefly explain what hydraulic background, and then you can explain what the valve we used. So what happens is when a customer designs this entire network, it has around 3,800 outlets. Each outlet is for, as you say, 5 hectares. So the hydraulic pipeline is designed for a condition that and all the outlets are open or all the outlets are taking water at a time. So you know, obviously the water being lifted, if one outlet is 8 lbs, the entire the flow which is being lifted is very, very huge, maybe for 16 cubics. Water is being pumped for every second. So what happens now, when come to the practical condition, all outlets are not running at a time. This is a practical scenario. And even 10% people are not using water. The variation in the flow being utilized will be very drastically dropped down. But your pipeline are already designed for your full flow. And now if the entire flow is dropped, what happens? The pressure in your system will start increasing. Okay? And no matter how beautifully you design, there will be situations, there are some zones, maybe say zone 5 or zone 6 are critical zones. And if that zone is functional with some other zones, the pressure which you need to achieve in order to deliver to zone 6 will be very high. So obviously for other zones, pressure will go very high. So we, I think along with Watmo team, their hydraulic team was involved in this project. They did all the scenarios, like instead of all these 8 zones are running at a time, only 2 zones are running, 3 zones are running, 4 zones are running, and they estimate you what is the pressure rise is going. And we found almost very 50 meters to 60 meters pressure rise, almost in entire branch point. So what happens if that branch point this much pressure is rising? When you go to the downhill, obviously downhill will be on a slope. So pressures in entire network is going up and up.
It's a very big area of 80,000 hectares. So in so many different crops, different stages of growth, and until the project will come to mature, it will take a lot of time. So we needed to run the scenario of 20% demand, 30% demand, 40% demand. What will be the pressure, and how can we reduce the pressure if it's needed by, you see the square blue station. This is the mega stations. So this is actually the upper network solution.
You can see the flow rates. These are the flow rates going to each zone, which is very huge.
It's about, each station is taking care of 2,500 hectares.
Yes.
And between 2 to 4 valves, 20-inch size, okay? And the red circles are actually the OMS that I showed you in the photo, okay? This is the outlets. Okay, I continue.
Now we can, now we'll see what solutions we give at. So we decided at every tapping, we will give this control station. And these are the, you can explain now.
Yes, so this is how the...
Sorry to interrupt, like this is memory spoon, they just have to change the card. Can they just do it for a couple of minutes?
Okay. So this is actually an alternative solution for BPT. Instead of constructing a BPT in the upper network, in those areas of critical zones, we suggested this mega station. Sorry. You can see that we provided air valve, strainers, flow and pressure control valves. Okay. Here the flow control was additional safety on the flow control that we have in the OMS. Okay. For these colossal cases that something really went wrong. Okay. And of course, quick relief we supplied here, 400 series, and Bermadi, you see Bermadi was involved also in the design of the station, okay? At the beginning we gave a flange-to-flange design, afterwards we even suggested a more hydrodynamic, less head loss design. At the end the customer chooses what he wants, but we supplied the recommendation. And you can see here that we give a full recommendation about the distances between the accessories, okay, the angle of the manifolds, etc., etc. And each station is connected to a controller. Maybe you can say something about this. It's okay?
Yeah.
Okay.
For the pictures.
You can see the pictures from the installation at site. We also have a very nice videos from there, but we can
One station, like that 24 stations are there. This is a picture before installation.
Yeah. I think already three stations are
Yes.
installed out of 24, and we continue this year, I hope. You can see that per each type of this project, which is huge in quantity and huge also in the size of the valve, etc., we design a 3D model in order to make the assembly perfect with no mistakes of the control loops, etc., and a 3D model of the valve. And each valve is assembled in Bermad, okay, calibrated and tested on the Bermad hydraulic test bench, of course with water, yes. And more photos, also from other places in the world, in which we are supplying upper network solutions, okay? You can see here a pressure sustaining valve at the discharge of a pump suction line, okay? Discharge line, sorry, it's not the suction, it's the discharge. So the pressure sustaining valve here are protecting the pump from overconsumption. We don't want to have a very high flow, and where you remember the pump curve, typical pump curve, we don't want to be in the right area where the flow is very high and the pressure is low, because the pump works very hard. It will go into cavitation damage maybe. So we want that when the consumption starts to be very high and the pressure is dropping, to regulate the valve, to make it, to modulate, to close, and not allow the pressure to drop more, protecting the pump from a very low pressure and high flow. Okay, this is one pressure sustaining, protecting the supply. Here we have pressure sustaining at the downstream of a filtration battery. When we backwash media filters, we have minimum pressure that we need in order to have an efficient backwash. Otherwise, we will go into iteration of flushing all the time. Okay? So, once we backwash the filters, then the pressure sustaining is operating, okay? And if the pressure is starting to drop to the set point, the valve will modulate to close, will total close, and will not allow the pressure to drop more in order to have an efficient backflush of the filters. Of course, if it needs to close completely and shut down the irrigation, it will do it, okay? So it's protect the supply again. And here we see pressure reducing valve in a very big project in Peru, almost Peru. It's a center pivot, if you know center pivots, irrigation machines, a project that we supply. And this is all Bermad tools that I talked about. Bermad air valve, allocating and sizing, Bermad sizing for optimizing the hydraulic control valves for the conditions in the system, Bearsoft, here you can see a design of an orifice for flow control, and search solution analysis.
Sorry, one question. Can we get these tools, like as designers or the contractors, can we get these tools for our own sizing purpose?
I think you can, but you know Micha. You need to get the authorization, and you will have certain level because you're not a Bermad employee or Bermad application engineer. But otherwise, if you need something more than the authorization gives you, then Pushkar will do the analysis. But yes, just write to me, and I will ask Bermad headquarters to open whoever you need. We give a certain authorization to part of our partners, of course.
Yeah, I agree. Like, if not all, even example in what mode we can have one login or a single person, and if not all, I'm not asking each and every one to.
I think Micha will not say no to you. So. dream about waterworks and irrigation. Let's talk a little bit about surge phenomena and surge protection solution when we talk about the area of the pumping station. Okay. So let's see what the surge can cause. Fun.
Oh my god. Oh, it's destroyed the back of his car.
Okay, so this is what we're afraid of when we talk about the ancient fear from a surge phenomena in a water system. Okay, so when does it happen? When a surge can be created, a water armor surge, it can be created when we are suddenly forcing the water to change direction or to change velocity. Okay, but it's something that happens suddenly. We cannot control it. And it happens very fast, okay? If we will do it moderate, it will not happen, okay? So if we look here, we have a pumping station and a rising main, okay? And now we have normal operation. We are delivering the water from the water source uphill to the reservoir, filling the reservoirs. And suddenly there is a pump trip, a power failure, okay? And the pump is tripping, is shut off suddenly, okay? What will happen to the column of water with all of its energy, with all its kinetic energy and inertia, it will continue to go up until it reaches the highest point. And then what we will see, the pressure in the main line, when the water are pushed up, the pressure in the line will drop. This is what we call the negative surge, the negative wave of the surge, okay? Because all the water are pushed up, okay? And the pressure is dropping in the line, okay? It could cause us pipe collapse, okay? So we need to treat it. And now, why the water are coming back towards the pump station? What makes them go back to the pump station? What force? Gravity. Gravitation. The guy with the apples falling on his head. This is what makes the water go back towards the pumping station and create the positive wave. The pressure is now increasing. At the end, the water column is meeting the check valve. And if the check valve is not already closed, the water will slam the check valve, okay? And it will create an additional surge, okay? What we call a secondary surge. So this entire phenomena, if we don't react to it, it will cause vibrations, it will damage the pipes, it can damage the pumps, if the pumps get a backflow, it damages all the components in the system, and this is what we are afraid of, okay? So when we are talking about power failure, which is unexpected situation, and in some areas, in some territories around the world, it's happening more frequently, And in other territories, okay, if we go to Sweden, they will say the last time we had a power failure was 70 years ago. So they don't worry about that. So when we talk about power failure, it's something that is emergency, and we need to react to relieve this surge, okay? But I want to say something in, how do you say it, כוכבית. In a little star, when we are in control, when we are operating normal system, and we shut the pump and we start the pump, we should not react to surge, we should prevent it, okay? So this is all the issue of pump control valves, okay? And we can talk about it. But we are, the approach is different when we shut the pump off and start up in normal condition, and when we are in emergency case, what we saw here, a power failure. Then we need to react, okay? Okay, so where in the water system we can see a rapid change in the velocity of the water. When it happens, when suddenly the water is changing direction, when we talk about pump shut-off and pump startup, but mostly critical on pump shut-off. Pump startup is not that dramatic to create a hammer and surge. When we talk about check valve, non-return valve, okay, that are not closed, that are not closing fast enough, we could experience a secondary surge when they are not waiting close to the column of water which is coming back. Hydraulic and manual valves, okay? We don't want them to close too fast, okay? And create a surge. Air valves, okay? If an air valve will release the air too fast, it can cause a slam and create a secondary surge. So we are talking all the time about the SP device, the surge protection device on the air valve that restrain the water, the airflow from going up too fast, from going out of the system. Okay? And of course, burst can cause a sudden change in the water direction and drainage. Okay, so we need to think about all of these scenarios. You can see here, I put here the wave velocity, okay, the surge wave velocity in different materials of pipe, in steel, in ductile iron, in HDPE, and in PVC. And you can see that it's very, very high, 1,000 meters per second flow velocity, okay, of the wave. So actually, we are doing 1 kilometer per second in ductile iron pipes. When we have a power failure and the water are running, they can run 1 kilometer in 1 second. So we need some solution that will react really fast to the surge, okay? Okay, let's look on this. This is some surge analysis, a graph of a surge analysis. When we have no protection from surge in a line in Jerusalem, you know Jerusalem, the holy city? So there are a few lines that were built in Jerusalem. This is, I think, the 5th line. It's a big line. And you can see here, let's look. We see here the static pressure of the system, okay? It's an elevated system. And you can see here the meters, the pressure in meters, head, okay? When we operate the pump, the dynamic pressure is of course bigger than the static pressure because we need to overcome the frictional head loss, okay? And now there is a pump stoppage, there is a power failure, okay? And the pressure is dropping dramatically, okay? It's still above 1 atmosphere, okay? But it's dropping dramatically. So the pipes experience low pressure, okay? And then it's increasing. So this is the negative wave that we talk about. All this envelope is the negative wave. when the column of water is pushed up. And this is the positive wave. You see here, the envelope of the positive wave when we're talking about the water of column coming back towards the pump station. At the end, after many oscillation, the pressure is stabilized on the static pressure again. But it causes a lot of vibrations, cracks, and can cause pipe collapse. So we need to treat this issue. Wait, sorry, it's too fast. Yeah, okay. So I want to emphasize that high points in the line will suffer mostly from vacuum conditions, okay? And during the surge, and low points will suffer from the positive wave, okay? So usually we will put an air valve on the high points, okay? Because air valve will intake the air in order to prevent the vacuum conditions. Bernard's solution is a combination of surge anticipating valve, and we will talk about that, and air valve. The surge anticipating valve is dissipating the positive wave, and the air valve are treating the negative wave and preventing vacuum condition and pipe collapse. When we talk about gravitational line, one of the things, the major thing that can cause us surge, not going uphill, now we're going downhill, is a control valve at the end of the line that will close too fast, and it could create a surge, okay? So in this case, what we should offer as a solution is a quick relief valve, okay? And we can also add features to the valve control loop to make the closing of the valve more restrained, okay? But anyhow, I suggest to install a quick relief valve at the end of the line. So let's look on the Berman solution and the traditional solution that is very common in India or applied a lot, which is the surge vessels, okay? So when we talk about the surge vessels, unlike the surge anticipating valve, the surge vessel is absorbing the energy. It does not dissipate the energy. What the surge anticipating valve is doing, they sense the drop in pressure when the water of column is going up. We have the negative wave. So one of the pilot, the low pressure pilot, senses the low pressure. It opens the valve, and the valve is already open when the positive wave is coming back. And then the water are discharged back to the water source, okay? And the surge vessel is actually treating both negative and positive, okay? It's a vessel that is partly filled with air, partly filled with water. We're taking advantage of the fact that the air is compressible, okay? And this is another solution that absorb rather than dissipate. I can say that if we already have a surge tank, or we are designing and we are going for the solution of a surge tank, if we will install air valve, it will minimize the volume of the surge tank that we are requiring. And you will see that one of the big disadvantages of surge tank is that they cost a lot of money. It's a big vessel made out of metal. It requires also space to put it. It requires maintenance, okay? And unlike the surge anticipating valve and air valve that require less space, near zero, almost no maintenance, no head loss, okay? So this is what Berman is offering compared to the surge tanks. You can see here, surge tank, I think from Argentina, okay, for a project. So think about it, when you have a lot of surge tanks, you need a lot of space, you need infrastructure. If there is an issue with the weather, too hot, too cold, you need to give it a special room to take into account the temperatures and the product cost. is much more expensive, 6 to 8 times more expensive than surge anticipating valves and air valves. And the space is not always available, and the issue of maintenance, okay? And this is Bermat solution. Already you can see here a pumping station, the water source, vertical pumps. Here we already have the air valves, okay? And this is the Bermat pump control valves that we talked about when we are in control, okay? Not in power failure. And here offline, you see the surge anticipating valves, okay? Once the positive wave will come back from the elevated point, the valve, this valve will already be open and will dissipate, okay, the water, the excessive water, the excessive pressure. This valve needs to open very fast, but to close in a restrained way to not cause another surge. Okay, so this is all applied in our control loop. Okay, well, I can talk more in detail about this. And you can see also the air valves that are equipped with the SP disc, with the surge protection disc. And once the water of column is coming back, actually the effect that the air is going in a restrained way, it's like a cushion that cushions the water that wants to push towards the pumping station, okay? And of course, once we have the negative wave, the air valves are intaking the air to prevent vacuum condition and pipe collapse. Okay, so they are doing two things, actually, the air valves in the case of the surge. Anyhow, in irrigation, you install air valves because you all the time fill up and drain the line, and you need during pressurized operation as well to expel the air bubbles, because it will harm the accuracy of the water meter, sensors, etc., etc. So this is a surge anticipating valve, Bermat 700 series. You can see that it has a low pressure pilot. This is the pilot that sends the negative wave, the drop in pressure, and makes sure that the valve will be open when the column of water will come back. This is the high pressure pilot, okay? When we sense the rise in pressure, because the water of column is coming again, it's opening even wider, okay? And relieving the excessive energy back to the water source, okay? We have a needle valve in the inlet to the control chamber. You can see here to make sure that we have a restrained closing, okay? And also we have here a mechanism with a needle valve and with two needle valves actually, in order to be able to calibrate the low pressure pilot. Because the low pressure pilot, we need to calibrate it to less than the static pressure. So we have to be able to get to this point, and we don't want to drain the line in order to do it. So we have a mechanism that allows us to drain just the sensing chamber of this pilot to be able to calibrate it to 70% of the static pressure. Okay? And the high pressure pilot, we recommend to calibrate at 110% of the dynamic pressure. So here you can see a system. We run here a surge analysis, okay? And you can see a graph of a system, the same line in Jerusalem, okay? The green is with protection. The green line is already with protection. This is the setting of the high pressure pilot, and this is the setting of the low pressure pilot. Okay? So once we have the pump trip here, this is the point that the power failure occurs, pressure starts to drop. When it's dropping below the set point of the low pressure pilot, the reducing pilot, the valve opens. It's waiting open for the water of column to come back, and it will take splits of seconds, okay? And the valve is already waiting open and starts to dissipate, okay? To dissipate the water. And you can see that the oscillations are much more moderate and very fast. We are stabilized on the static pressure, back to the static pressure. Between the setting of the high pressure pilot and the low pressure pilot, between the red and the blue lines here, dashed lines, the valve is closed. So in normal operation, when we don't have this issue of power failure, pressure is dropping, the valve is closed. Okay, it's not bypass. It's offline. It's told offline. Okay, it doesn't. You see here, it doesn't interfere with the system. The flow direction is from the pumps through the main line to the field. Okay, and the flow direction in surge will be from the reservoir back here through the surge anticipating valve back to the water resource. Okay, is it clear? You have question? Okay. So just a short summary of all the solutions, traditional solutions that we can see in India and compared to Bermad offering. In India we see zero V valves, it's like a very quick check valve. We see traditional air valve, controlled NRV that allow us to let the water go backwards towards the pump in a controlled manner, and the surge tanks that we all know. And Bermad solution, a combination of surge anticipating and air valves, okay? And it is 6 to 10 times less budget for Bermad offering. It requires near zero maintenance, it's approachable, and it has require low space, okay? And no additional head loss. It's installed offline, doesn't interfere with the system when it's operating in normal conditions. You can see here some installations. Vidit, maybe you can elaborate on the installation at the site of surge.
So the first pic which we can see on the left side is from Jalna MJP, where a surge anticipating wall of 4 inch was proposed. The second image is, the center one is from Chitradurga, Karnataka. Now this is a live case study which Bermad did. Like the entire rising main was in the running condition, and all the joints and fittings were coming out of it. So Karnataka Water Board approached Bermad that what can be done for this, because every alternate days or every 2 days they had to do a shutdown to repair it, make the joints and fittings again install it, and so that the water is provided, and whatever the villages or towns are there, they were getting hampered due to this. Previously some pressure relief wall was there, but due to wrong engineering, wrong installation, plan was good, execution was bad. There was a surge protection device. It is not like that there was not a surge protection device and still it was breaking. But it was not installed in the correct position. The sizing, first thing. Second thing, the sizing was not done correctly. And the third thing, the characteristics of the wall like PN rating and the wall pilot settings were not done correctly. So these three important things, because it was just like, you supply and go back. Like what Leo said and what Sarit said, that it is not like give me an inquiry, I will give the quotation, I will do the negotiation, okay, bye. It is not like that. Bermad doesn't believe in that. Then they approached us, obviously with the help of our Israel team. Pushkaraj did the surge analysis, complete surge analysis, a fresh study. We were considering it as a fresh study. And then we took their approval, we explained them what the condition is. It's now almost 3 to 4 months the line is running successfully, because the sizing was done, engineering was done properly, wall selection was done properly. And you can see it is not only the surge anticipating wall, the one with the grey cap, you can see a Bermad air wall also here, and there are other air walls also. The photo is, it is cropped. So this is a very good example which recently we did, because usually the surge study in India or surge projects in India are not more of a live project, they are done as an operation and maintenance project. Okay, so until unless something gets burst out, no one thinks about search. So that has happened here. This is a real case study 6 months back. And similarly, this is an old project, Nanjangood and Gadak, that the last two green ones, those are irrigation projects. This is a water supply. These two are the blue ones are water supply projects.
For now you said the sizing was not done properly. So what are the factors you considered when deciding the size of the wall?
Generally, for surge anticipating wall, as you see, two main factors is the low pressure pilot setting and high pressure pilot setting. These two are main parameters. Along with that, every well has its KV or percentage of opening or its resistance, and it has its response times. So we use softwares like KY Pipe, or we can use Indian software like SAP. So these softwares are built to take these inputs. When we select, there are surge protection devices. So when you use a device called surge anticipating well or a hydraulic SAV, so this software will ask all these inputs. So obviously these valves inputs will depend on client to client, vendor to vendor, which product we are utilizing. Again, same for combination air valves. There is a anti-slam disc, as Sarit told. So this disc has some hole diameters. Okay, so that will decide how much air flow or air intake has been taken. So these diameters of the disc, air valve disc, and the settings of the SAV, this we need to feed into the software, and we analyze, we do the iterations and simulation, and then we arrive the sizing. Again, we also for SAV, as you see, this is a very quick response. So the volume of water which is being released or dissipated through these valves is very high. So we generally take very high velocity because this valve is going to run for a very small period of time, like 1 minute or 2 minutes. So we generally consider a velocity of 10 meter or 15 meter per second, and based on this we will generally arrive the sizing of the SAV. Also, we suggest not to go for single SAV. Generally, we provide two, so that to have a good redundancy for the project.
So actually it's the complete surge analysis, all the data that we need from the client about the pipeline profile, diameter flows, maximum flow, low flow, everything we need to know, the topography of the line. We are putting everything inside the KY pipe, and we're doing the full surge analysis in order to size, allocate the air valves, choose what type of air valves, where to put it. So it takes a lot of experience and to work with this kind of software for a long time. And Bernat has this experience. Other companies, of course, have it as well. But I'm saying as you have more experience, then you do it better. Okay? This is another installation of in India pump control and surge anticipating valves. And this is the pump control in Nanjangood, okay? 12-inch. I say one last sentence about pump control, and we can go for the reservoirs application. Pump control, as I said, it's to prevent surge and water hammer when we shut the pump in normal operation. The main concept is to isolate the pump from the rest of the system when we start the pump and when we shut the pump. So this is a solenoid operated hydraulic control valve connected to a controller, and when we start the pump and we shut down the pump, we make sure that the valve is closed, isolating the pump from the rest of the system to not cause vibration and water hammers during normal operation. I will not go into more details about this. Do you want to do the reservoir management now? Yes, I think, yeah. until we fix, I want to say one more thing about Bermat air valve, which is important. In many tenders in India, the air valves are specified according to a diameter. But if you will see different air valves from different manufacturers with the same size, you will realize that one is a full bore and it has a big inlet to the air, okay, and one is a reduced bore. So actually, the correct way to test what air valve will be correct for our system will be according to the performance of this air valve, okay? According to the capacity of the intake flow of air, okay? So I can tell you that Bermat tested 13 different manufacturers of air valves for the same size, 3-inch size, and we can see that the lowest air valve that has the lowest performance, okay? It can intake air of 500 N cubic per hour, okay, air, and Bermat air valve, okay, C70 in a certain pattern. We have mushroom, we have side, can go up to 2,000 cubic meter per hour air, okay, in the same size. So it will be more correct to put in the tender what flow of air you require to intake into the system, and then you will get much more cost-efficient solution for your system, okay?